Welcome back. This is Static Electricity Day 2, and we're going to be taking a look at two-dimensional Coulomb's law problems today. We're going to begin on number 5 on page number 10. So go ahead and read the problem. Charge A is at the origin, has a charge of -2 times 10 to the -9 coulombs. Charge B is at -3 meters on the y-axis and has a charge of 6 times 10 to the -9 coulombs, and charge C is at 4 meters on the x-axis and has a charge of 5 times 10 to the -9 coulombs. Find the magnitude and the direction. So let's take a look at this. Go ahead and label all the givens. So I've labeled the appropriate charges and distances that we need for this problem. And Coulomb's law is always going to involve just two charges. So the first thing we're going to do is we're going to figure out the force that B exerts on A. And then we're going to figure out the force that C exerts on A. And then we'll simply add those together to figure out the net force on charge A. So here we go. Coulomb's law, the force is equal to K, Q1, Q2, over the distance between them squared. So 9 times 10 to the 9th. We'll put the sign in later, 2 times 10 to the -9. 6 times 10 to the -9. All over 3 squared. And go ahead and type that into your calculator. And we get 1.2 times 10 to the -8th newtons. And now we want to figure out the direction. So A is positive, B is negative, so they're going to attract. So if they attract, A is going to be pulled down, B is going to be pulled up. But in this case, we only care about the net force on A. And A is being pulled down. The next thing we have to do is figure out the force that C exerts on A. So the force that charge C exerts on charge A is, again, we're going to find it using Coulomb's law. Charge C is charge 5 times 10 to the -9 over 4. So we have the constant, 9 times 10 to the 9th, 2 times 10 to the -9 is the charge of charge A, and 5 times 10 to the -9th is the charge of charge C. So go ahead and type that into your calculator. And we get 5.625 times 10 to the -9. And the direction. So we have a negative and a positive. Okay, so they're going to attract. So charge C is going to be pulled to the left, charge A is going to be pulled to the right. But again, we're only finding the net force on charge A. So when we're asked which way does that exert a force on A, the answer is going to be right. And then right away, you're probably realizing, wait a minute, down and right. How do I add down and right? Answer, vectors. So what you can do, you're going to go right and then down. And so our right is 5.625 times 10 to the -9. Our down, remember down you have to make a negative in vectors. 1.2 times 10 to the -9. And we need to find the hypotenuse and we need to find the direction. So the hypotenuse, you're just going to use Pythagorean theorem. So plug that into your calculator. So 5.625 times 10 to the -9 squared plus 1.2 times 10 to the negative. And you find the magnitude of the resultant using Pythagorean theorem, and you get 1.325, we'll call it 3, 1.33 times 10 to the negative 8. And then for your direction, remember the direction of any vector is given by the inverse tangent of its y component over its x component. We will have to correct for quadrant here. Remember, we're in quadrant 4. So unit circle, we have 180, 360. So in this area, quadrant 4, we know it has to be between 270 and 360. So since it's going down to the right, it's definitely quadrant 4. So let's go ahead and plug that in. You must do y over x. You must have the negative signs. Negative 1.2 times 10 to the negative 9 over right is positive, so we can just do the 5.625. Oh, sorry, this was negative 8. I wrote 9. The top one was 9. Nope. Let me correct that. So I had a mistake in the exponents here. I think I had 9 on top and the 8 on the bottom. And I've corrected that here. So it's negative 1.2 times 10 to the negative 8 over 5.625 times 10 to the negative 9. So when you do that, you are going to get negative 64.9. And remember, you're going to have to correct for quadrants. So when you add 180 to that, that's going to put it in quadrant 2, which is 115. And that's also wrong, so you're going to add 180 to that. And when you get that, you will have 295. So there's a slight mistake here in the key in terms of the angle. Although I should point out that the amount of decimal places that you include can very significantly affect the angle. So we had 290, 2.6, and 295. That could just be a matter of how many decimal places I used when I did this problem initially. Here we have another two-dimensional Coulomb's law problem that we can do as practice. So charge 1 is 2 microcoulombs. Charge 2 is negative 3 microcoulombs. Charge 3 is positive 4 microcoulombs. And charge 4 is plus 5. So we'll go ahead and just label our distances now. So I've labeled all the givens, and now it's just a matter of using Coulomb's law to find each of the forces. So let's find the force of Q2 on Q1. Q1 I'm going to put next, since that's going to be the same in all our problems. So a micros times 10 to the negative 6. And 3 times 10 to the negative 6. All over 0.3 squared. Now, before we do any math, I can tell you right away that these two are going to be attractive. Because Q1 is positive and Q2 is negative, we know opposites attract. So we'll just plug that into our calculator. And we get 0.6 newtons. And that is going to be right. Q3 and Q1. So I'll change colors here to try and keep this organized. So it is going to be 9 times 10 to the 9th. 2 times 10 to the negative 6. And Q3 is going to be positive 4. So 4. The distance between them is 0.4 squared. Now we have a positive and a positive, so they are going to repel. So this is actually going to be an upward force. on Q1 because we're just finding the net force on Q1 in this problem. So you just type that into your calculator. And we get 0.45 newtons up. And then the last one, 9 times 10 to the 9th. Charge 1 stays the same, still 2 times 10 to the negative 6 because it's microcoulomb. And this is Q4 this time, so it's 5 times 10 to the negative 6 all over the distance between them, which is 0.3 squared. So go ahead and plug that into your calculator. And right away we have a positive and a positive, so you know that they are going to be repelling. So it will push Q4 to the left, Q1 to the right. We're finding the net force on Q1, so that right is correct. So go ahead and type that into our calculator. And I get exactly 1 Newton right. So now we have to add it and figure out what our net force is. We'll just do an XY chart like we did in the beginning of the year with vectors. All our x's, all our y's. So the first was 0.6 newtons right. Right, of course, is x-axis, and right is positive. So right plus 0.6. The next was 0.45 newtons up. Up and down, obviously, would be y-axis. So it's going to be plus 0.45 on our y-axis. And the last one was right. Going to write plus 1.0. And we only had 3. So those are our 3 components. We're simply going to add them up. I get 1.6 on my x and 0.45 on my y. So when I sketch those, I get 1.6 and I get 0.45. So I just need to use Pythagorean theorem to find the magnitude. And we are going to get a magnitude of 1.66 newtons. And then to get my theta, my angle, this is in the first quadrant, so whatever it gives us is actually going to be the answer. Plus 0.45 on the y, plus 1.6 on the x. So the inverse, and that is 15.7 degrees. So my answer, the force, the net force on Q1 is going to be 1.66 newtons at 15.7 degrees. So there you have it. That's how we find the net force when there are 4 charges. Okay, we're going to take a look at some conceptual questions that involve Coulomb's law. What happens to the force between 2 charges if the charges double, both charges double, etc.? So the way that I would have you do this is the way we did earlier in the year, essentially plugging in dummy numbers. So we know the force is equal to K Q1 Q2 over R squared. So K is never going to change. So right away you know that's going to be a 1. What happens to the force between 2 charges when one charge doubles? So one of the charges doubles, so let's say that's Q1. Put a 2 in. What happens to the second charge? Well, it doesn't say anything, so I assume it stays the same. What happens to the distance between them? It doesn't say anything. I assume it stays the same. So it's going to double, because 2 times 1 over 1 is just 2. Why don't you go ahead and try plugging in the each of the scenarios and see what you get, and then we'll go over them. So number 2, what happens when both charges double? So both charges double. Charge 1 doubles, charge 2 doubles, distance between them stays the same 4 times. What happens to the force between 2 charges when the distance doubles? So charge 1 stays the same, charge 2 stays the same, the distance between them doubles. It's going to be 1/4. What happens to the force between two charges when both charges are halves? If the first charge is half, the second charge is half, the distance between them stays the same. That's also going to be 1/4. What happens to the force between two charges when one charge is half? So 1 times 1/2 over 1 squared. It's going to be halved, and when the distance is halved, so first charge stays the same, second charge stays the same. The distance is halved, so you're going to have 1 over 1/4. Well, 1 divided by 1/4 is 4. So it's going to quadruple. So number 7, what happens to the force between two charges when the distance is halved and one of the charges is doubled? So we have 2 times 1 over 1/2 squared. So we have 2 on the top, we have 1/4 on the bottom. Division is multiplication by the reciprocal, so we have 2 times 4 over 1. It's going to be 8 times. What happens to the force between two charges when the distance between them is doubled and the strength of one charge is doubled? The distance between them is just doubled. So we have 2 over 4. It's going to be 1/2 of the original amount. What has a bigger effect, the force on the force between two charges, having one charge or doubling the distance? So in scenario 1, we're going to halve one charge, leave distance alone. The net effect is half the original amount. The other scenario, we leave both charges the same, and we double the distance. 1/4 of the original amount. So which had a bigger effect? Well, this one cut it in half, this one reduced it by 4. So I would say that doubling the distance has the greater effect because it is 1/4 of the original amount. What has a larger effect on the force between two charges? Doubling both charges or halving the distance between them? Well, let's see. So doubling both charges, so 2 times 2, 1 squared, 4 times. Halving the distance between them. And the effect is they have the same, both will quadruple force. So this is how you use Coulomb's law to predict what will happen to the force between two charges if something happens to distance and or one of the charges.